So one of the things that I wanted to do is to show the experience of H2O inside of R. I have a 2-hour hands-on tutorial. I'm going to go through 3 different aspects of the software. One aspect is what we're calling the basics, which is really data I/O, as well as the ability to do some data munging or manipulation. The second part of the talk is going to talk about 4 types of advanced analytics that we have. I'm going to be talking about generalized linear models, gradient boosting machines, random forests, and I'm going to give a hint to deep learning, which Arno is going to add more content to as the day goes on. And I'm going to show about them in a regression and classification context. So I first want to introduce these algos to you, and then we're going to do a hands-on tutorial. Now, as I mentioned, I have 2 hours total to go through this. So what I can do is give you the experience. What I'm not going to be able to do is to get to necessarily the level of detail that you might need to do an analysis. We have the Elements of Statistical Learning book on display here. There will be a book signing by Trevor Hasty later on. And in that book, there will be a lot of content that you'll want to have in order to do your analyses. But what I will do is show you in H2O how each of these algos work, and give you a hint about how you can explore the model space to draw reasonable inference on your data. So with that, I'm going to start the process here. And I'm going to start where many of you have started already with the virtual machine. Now, I'm going to be working in the same environment you are, the virtual machine. I also have H2O installed on my local machine as well. But I want to have a common environment. And for those of you who may have been struggling with the virtual machine, do feel free to use what you have locally, or even if you find what I'm doing not 100% relevant and you wanted to play around with H2O on your own data, we encourage you to do so. So this is starting up. I'll wait till this thing kicks off. All right, so now I have my instance, which is my virtual machine. Let me see if I could blow it up a little. There we go. OK, so here I am in my virtual machine. I move my icons around a little bit just to make them easier to find. But I'm gonna start with an RStudio. Well, maybe what I'll do is just give you a little orientation here of what's on the machine. So I'm just going to click on the computer icon here. So if you look in the file system, there are a number of folders here. The 2 folders that are going to be relevant to me are the data folder, because that's where all of our data reside. And if you scroll down, there's also, well, I guess H2O tutorial is off of my home directory. So if I go into home, H2O, there's the training material. So those are the 2 most relevant locations for files that we're going to be looking at today. So I'm going to go ahead and start up my RStudio session running the latest version of R. And all that I'm working on here is essentially a mirror image of what Amy had done earlier today. So what you saw Amy do, where she had an H2O cluster up and running, she had her web browser open, and she was hitting the H2O cluster. I'm going to be doing something similar to it from R. You could just think of these as two different ways of interacting with the same H2O cluster. There's going to be nothing special happening here on the R side when I use H2O. I'm going to use it to start up a cluster for demo purposes. But in a real-world situation, what you'll have is a cluster up and running. You'll start up your, if you're an R user, you'll start up R, and you'll connect to the cluster, and you can do operations on it. But I'm not doing anything R-like, on the cluster side. This is just interfaces. Okay. Let me make it bigger. So I'm going to make my font bigger, and if you're having trouble seeing stuff, let me know. And I apologize, I was in the back row, and I don't know how you folks in the back row can see much of anything. So it's one of those things where you have to sacrifice. So if I make it bigger, I'll try to find a compromise font size. So how is this? Is this font okay? Is it okay? Okay. So what I'm going to do, as Arno showed, all this stuff is available. It started out on GitHub. It's now on your virtual machine, on your sticks. But what I want to do is I'm going to open a file that contains this neat R markdown hybrid. So it's not the standard markdown file in R, because we essentially wanted it to be able to serve two purposes. One purpose is to just run it as a script, and the other purpose is to build a nice, pretty document. So if you look here in my nav breadcrumbs, you'll see that it'll say H2O off of my home directory, H2O training, tutorials, and this is our home base for all of the scripts we're going to be working through. H2O training tutorials. Everything is there. And I'm just going to be going through some of these. Arno will be going through some as well. And you're free to explore this at your convenience. But I wanted to let you know that this is the most important place to find your scripts. So I'm going to start this up. So here's my R script, and you can click on this to show a pretty version of this script. You can also, there's the docs version as well. And what I'm going to do first is, I think, look at it from this perspective and then get into the R script, because I want to make sure that you're able to see where the big picture is in all this, and as well as the nitty-gritty. Because one of our goals is, at the end of the day, you feel productive in H2O. You might not have all your questions answered, but you feel that you can take the material that we've given you, and you know where to start to answer those questions. So one of the things that we're going to do, and let me maybe blow this one up a little. Hopefully this font is big enough. We're going to load the H2O package. This package is both available on CRAN, which is the Comprehensive R Archive Network, as well as the H2O AI website. We're going to load this package. We're going to start a cluster. Now, if a cluster had already been started, this command H2O init will, if I provide it with an IP address and a port, it will connect to an already up and running H2O cluster. Here, when I do it this way, it's going to start one locally. So just high level now, what do I want to do? Well, what I want to do is the standard thing that you find yourself with when you're doing a data analysis. You find your data, you load it you manipulate it, you get it into a form that is ready for analysis. So that will be the first third of where we go. And just to make things somewhat familiar and also to deal with data that's publicly accessible, I decided to mimic a data set that you might have encountered already. So at the University of California, Irvine, they have a nice machine learning repository of data sets. One of those data sets is the adult, they call it the adult data set. And it's a data set containing census information from the mid-1990s. I wanted to take a data set from modern times and try to get it into a position where we can analyze it. And so that's what's going on here. Just to orient you as to what I'm doing now, I have a data set that I've actually, they have a 1% sample data. So that means, 1 out of every 100 people is represented in this sample. That, unfortunately, was too big for the virtual machine. So I did another reduction on that. So we have basically 1 out of every 1,000 people being represented in our sample. And then I'm going to go through the process of reading it in, examining what I get after I read it in. So this is going to go directly from storage to my cluster. And the storage happens to be a comma-separated file. Oh, I just realized I should kill this. Oh, hopefully nobody sends anything. So we're going to create this data set, and we're going to do some manipulations to it. I want to calculate, well, first I'm going to calculate some summary statistics. Then I'm going to derive some data columns, which is very common. And I'm also going to, after I do my data derivation, my column derivation, I'm going to create some training and test data sets. And then finally, I'll be ready for my analysis. So let me go back to my R session now. So remember, we're going to read in data, summarize data, manipulate data, get data ready for analysis by creating a training and test split of my data. And if anyone's having any issues, please raise your hand, and people will be circulating to help you out. So this is the coolest part in my mind, where all I need to start up. Oh, wait, I guess we have a question. I'm sorry, what?
Not all people have the data sets. So if you point to S3, I made the H2O training data sets public.
Oh, you made it public?
So that bucket is public, so people can link to. Most of those data sets are not massive, less than. So if you go to S3 on Amazon, so just log into the Amazon, and H2O-training is the bucket name.
Oops. It's H2O-train?
Yeah.
Slash
airlines or slash.
I'm sorry.
Slash airlines, or you have.
Oh, airline. Okay.
Whole folder is.
All right. So like slash. In this case here, we're going to be looking at. Slash airlines.
I think Prithvi is hacking a static page for it, but for that bucket, so you can use the whole URL for your URL for your data set.
Yeah.
Prepended with the bucket name and the.
Oh, okay. So I actually, hold on, let me look here, because I'm sorry, let me. It's easier for me to look at it this way. So we're looking at H2O training. And then, well, for my situation here, the data set I'll be using is it's this data set here. So let's see if there's an easy way to communicate this. I don't. What am I missing here? H2O training, 2013. Oh, I'm missing an underscore. Sorry. So I don't know if you could see this URL here.
Slightly bigger.
All right, you can go to s3.h2o.ai. That creates the forwarding you need to all those files.
Where is it, Arno?
s3.h2o.ai.
Oh, h3.
It's just the S3 subdomain.
H2O.ai. Okay, perfect. So s3.h2o.ai. Now you'll have to tease these apart into to get them to work with the scripts, but at least now you can grab those. So that URL again is s3.h2o.ai.
Just make them slightly bigger on the screen. We can just see.
So, what?
Yeah, yeah. So people can see the data sets. Just a second. Yeah.
Okay, we good? All right.
Just had a question over here.
Yes.
So when we loaded the package H2O, there's a message saying if else max min are masked by the H2O package.
Yes.
So does that affect our other code that already uses?
So what we did, there's a question having to do with when you load the H2O package, a warning message pops up that says that certain functions in the R base package have been masked. What we did is we created S4 generics for those. There is a potential for a collision if you have another package that does something similar. But if you don't have that type of situation, it will be fine. So the answer is it depends. All right, so with that, I'm going to get back onto the script. One second here. I want to go bigger. All right, so here I am. I'm back in my script. I started my cluster. And now I want to do, so one of the things that you can see here when the cluster started is that I got some information relevant to my, my cluster. So here I have the version of H2O that's being run in my cluster, the name of the cluster, the number of nodes. In my case, it's just the virtual machine, which is a single node, the amount of memory, which is a little less than a gig, and how much compute I have. So I got 4 cores, all of which are allowed to be used by my H2O cluster, and the cluster is in a healthy state. So now I'm going to read the data in. And there's a function called H2O import file. And the way that, so I'm using RStudio here, and I'm using an RStudio convention of being able to send blocks of code over from the script to the console by selecting the text, holding a control key down and hitting enter. Just a convenience. So if you see me start to highlight stuff and magic happens and code starts running, that's what I'm doing behind the scenes, is I'm holding the control key down and hitting enter. And so here you see this loading up, and this parse is actually very fast. Once you start to explore your own data, you'll discover how quickly you can get the data up into your cluster. Running on a virtual machine, things are a little slow because of how things go. Yes, question? Yes. So what's going to happen now is, provided you have enough stored, the question was, where do the data go when you read them in? What's happening is, once you do this, this import, it's going to read the data, parse it, and it's going to hold the data in memory in your cluster, provided you have enough room to house it there. And that is where you're going to get a lot of your performance out of. And as Cliff mentioned earlier today, it's going to be in a compressed form. So not only is it going to be readily available, it's going to be easier to navigate because of the fact it's compressed. So I've now read in my data. And I'm just going to look at some aspects of it. So here I have in my data set, so there's a way of essentially looking at the directory inside my key value store that Cliff mentioned. It's the H2O ls function. And here I can see that I have one entry, one key, and it's taking roughly 100 megabytes worth of space in my cluster. And when I read in the data, what happened was it created a proxy object to that entry in the key value store. And the proxy object inside of R is called H2O parse data. That's the class that it has. But it's going to behave a lot like a data frame for those who are used to being in R, or you can just think of it, it'll behave a lot like you would expect a table to behave in a mathematical computation environment. I can use, because it's intended to behave like a data frame, a lot of the capabilities of a data frame are available at your disposal. So you can go and ask what the column names are, what the column's dimensions are, and you could play around with that. The first thing I'm going to do is I'm going to select out a subset of the data that I'm going to be working on. Because remember, as I said, just for familiarity, I want to recreate the adult data set that's contained in the UCI machine learning repository. And I don't need all the columns that are present in my data set. So I'm going to extract out the columns that I need. And for the purposes of this exploration, we're going to be studying how much people get paid under various conditions. And so we're only going to be looking at those set of people that actually have earned money over the past 12 months. And that's what's happening here. There are two operations happening. One is a row filtering operation, and the second one is a column selection operation. And this is happening using R's square bracket interface. But again, this is all happening on the cluster. Nothing is happening. It's all the same machine, but it's happening inside H2O's memory space as opposed to R's memory space. And since we have a key value store here, I like keeping things kind of clean, and I'm just going to name this appropriately. I'm not going to get too deep into this, but I did want, for those of you who go through the process of exploring what is it that I have in my cluster, you can always give things a name in the key value store. If you don't give it a name, there'll be a machine-generated name. And so if you looked at the cluster, you might be, well, where did this thing go? And that's the exercise that you see happening throughout this script is I want to make sure that it always seems very clear as to what's happening with your data on the cluster. And so now what I'm going to do after I read the data in, after I've selected my subset, just to get a summary of this. Now, earlier in the day, Amy showed how to do a summary from the web UI. Well, you could do the same type of summary from R. And it's using the same technology under the covers. There's nothing, like, oh, I used R or I used the web UI. It's all the same, regardless of interface. So here I could see that I have 12 columns. The dim function tells me the dimensionality in a 2D form. So how many rows, how many columns? So I have roughly 150,000 rows and 12 columns worth of data. Now, in real-world situations, you're going to have much larger data sets. But when you're operating on a virtual machine, you have to be conscious of the fact that it's not always easy for you to get a virtual machine in this type of environment on your laptop. You're fighting with the operating system sometimes, locally. So we kept it small, short end of it. Now what I could do beyond that is do things like calculate quantiles. And quantiles are a way of finding out a relative percentage-wise where certain values lie. So here what I'm doing is I'm finding it at 100 different locations, equally spaced. So going from 0 to 1. So I'm going to get percentiles out. So what is the value for which 1% of the wages are below? What is the value which 2% are below? So on all the way up to 100%. And this quantile is done very efficiently. And for those of you who have tried to play around with things relating to order statistics and things involving rank, this is not easy to do in a distributed environment. And for those of you who want to know what's happening behind the covers, Cliff has put together a little hacking session relative to it, so you can learn more about the exact algorithm that we're using. It's not as simple as just calculating an average or a standard deviation. You have to have more understanding of the data than just simple aggregates. So I'm just going to, all right, so I did that quantile calculation. I wanted to show this if-else function because it's extremely useful for deriving conditional columns based upon conditions within your data. And so here, what I'm doing is I'm taking on the column that has how much income was related to interest and dividends, and I'm going to split it into two separate columns. One column I'm going to call capital gains, the other capital loss. And again, this is to mimic what was in that UCI data set. And the condition is just whether or not there was positive or negative income associated with interest and dividends. Very, very simple. And then I'm going to drop off that column relating to interest and dividend payments. I'm going to just, again, give it a friendly name in the key value store. Another thing I might want to do is take the log transform. Let me see if I can play with real estate here so things aren't wrapping so much. So you could do all the nice math functions you'd want to do. A very common transformation is log. So This tends to be used in a situation where you have skewed data. And that's the case when it comes to income, either through wages or through interest and dividends. Nothing special there. Your math functions are available to you. So we showed how you can use conditional derived columns, how we can do math derived columns. Now what if you want to take a numeric column and bin it into categorical columns? We have an H2O cut function to do that. It mimics the cut function in R. This is, I find, very useful to do in different modeling contexts. So you can decide, in a lot of the algos that we do, the algo might decide where, like in the tree-based settings, the algo decides where the binning might occur. Well, you might want to bin it yourself, maybe for more interpretation purposes, or maybe you have some theory for why certain numeric quantities should be grouped together in a category. You can use the cut function to do that. And then I'm going to do some tabulations. And so you can do crosstabs well, here this is a simple table of taking a single categorical column and tabulating it. I can also, here's another one, simple tabulation. I can also do a cross tabulation where I'm looking at two quantities. I'm just going to walk through this. So there's a lot of examples of doing crosstabs. And again, this is all running on the cluster. There was a question earlier today about data types. If you want to change, so lots of times in your data, you might have integer coded data, but that integer coding might not represent the number one, but category one. And in order to change that representation in the modeling, we follow the R convention of using the as.factor call to flip it essentially from, hey, interpret this as an integer, to, hey, interpret this as a category. Then I'm just going to do a few more things and we'll get to modeling. One has to do with interaction effects. An interaction effect in a linear modeling, well, in any modeling case, but for other models, this has happened by the algo. But an interaction is when you look at two columns and how they interplay together relative to some target variable that's of interest. We have a function that allows you to generate that interaction, that combination from H2O. And so I just generated that column, and I can go through the process of looking at the results in the key value store. I can also do some further aggregation using a ddply-like. So for those of you who are using R, you've probably heard of the plyr package and the ddply function that's contained within it. We have an interface just like it for doing the same thing. For those of you who don't know R that well or haven't heard about plyr, all we're doing is group by summaries with this function. So you want to do your aggregations based upon some grouping of the data, and the code is contained here to show you that. And finally, I'm going to create my test train split. And the way that I like to do it is I like to get a sense of what went where and why. So what I'm going to do is I'm going to generate a bunch of random uniforms on the cluster now. And I'm going to use those random uniforms to decide which data set we're going to be looking at. Does that row belong to the test set or the training set? And we're going to have 75% being in the training set, 25% in the test set, and we'll be good to go. And then we can look at the division that results from that. So I have roughly 150,000 rows, 100 and 12,000 went to my training set, 37,000 roughly went to my test set. So I now have data that are ready to analyze. And then I could just look at, like where I am in terms of what I have. So what I was able to do now in H2O is just prep my data, get it ready for analysis, do some last mile manipulations prior to modeling. Are there any questions about what I just covered? Yes, in the back.
And convert it to our data frame, right?
I'm sorry, I missed the first half of your question.
So I was asking that it is possible to import the data as H2O data and convert it to our data frame, right?
Yes, yes. Yeah, so
if the data, so the question is this: if the data is very big and it needs to be distributed over a few machines, when you convert it to our data frame, what happens to that data frame? Still, this data frame is distributed or no?
So the question has to do with how do you essentially bring the data into an R session? Now, what's going to happen in that situation? Well, the function you're going to be using is the as.data.frame method on an H2O parse data object. Well, it's going to try to bring all that data into your local R session. If you have enough resources in that environment, it will bring it all into it. If it don't, it'll probably error out for you.
So the reason that I asked this question was I was thinking that, for example, if there are some functions that are not supported in your R API or in your R package, whatever, I was thinking that we can import the data, convert it to our data frame, and then do whatever we can do in R on that data frame. But with your answer, it looks like that we cannot do that, right? If the data is big enough, if it is very big that we can't put it in memory of the machine in one node, then we cannot do that.
Well, yes. So if you want to deal with the full data set and in a single R session, and that R session can't handle it, but what we don't have a utility, it sounds like what you want is now write everything in a way that's consumable to lots of little R sessions.
Yeah, okay, thank you.
Yeah, we don't have that tool. It's not that it can't be built, it's not currently in product. Yes, question. Oh, yes. So the question had to do with why in the R UNIF function call did I specify the data set. And the reason is I want to create, and this is just an API issue, but I want to essentially create a column of random uniforms that will be compatible with the data set I supplied. And one thing would be that it would have to have the same number of rows. So it's just an API convenience to do it that way. Yes, question. On line 2.1? Oh, line 1. 91. Yes?
So can you just explain how it's doing the assignment? Is it adding an extra column in the H2O store?
Yeah,
That's the syntax in H2O?
Yeah, so the question has to do with when we're adding a new column into the frame, what are some of the underlying details? And in fact, Cliff had touched upon this a little bit in his talk earlier in the day. So when it's making this association here, what it's doing, at this stage here, it's just in the proxy object associating them together.
Is that a copy of the whole column at that stage?
So am I copying it at this stage? No, it's a reference. Is there a question?
Yeah, is there any kind of conversion tool if I have an existing base of R code, some things that are already running, to convert it into kind of the H2O functions, and so it'll run that way? Or if not direct conversion, some kind of help?
So you want to, the question has to do with whether or not you could take existing R code and bring it over to work on an H2O object.
Yeah, I mean, I can imagine doing it manually. Is there any kind of automated assistance or
well, there's no
tool?
automated tool for that. What we've tried to do is have APIs that would be similar, or if not identical, to what you would do for a data frame.
Okay. Just a suggestion might be helpful to have some kind of lint scanner, at least to identify, these lines you might want to convert to H2O or something.
Yeah, I mean, that's a nice tool to have.
Okay.
Correct. Okay. If there's no other questions on this section, I'd like to move to the modeling piece. So one of the things I want to do is I'm going to just start a fresh session here. Just to make sure that I don't have any interference going on. So I'm just going to start a fresh RStudio session. And, oh, this isn't what I want. And what I had done to introduce a lot of the algos is just to have a very, very high level look at what it is that we have inside of H2O that you can use. And I left off some of the very low-level details because lots of times those are specific to the types of problems that you have. But as we walk through this, we could talk about what we have, and if there's any questions that you have along the way, let me know. So now that we've gotten the data ready for analysis, we want to go through the process of analyzing it, and we're going to highlight 3 algorithms at this point. Generalized linear models, gradient boosting machines, and random forests. We're going to look at the implementations inside of R. For a deep understanding of that, we have books that you can look at, but I will talk about the implementation details that we have for R. Yes? So this MD file, I was a little fast with this one, and I apologize for that. So I went to H2O, H2O training, tutorials, supervised. So we're now looking at the supervised learner space. And in that folder, you'll see some algos, generalized linear models, gradient boosting machines, random forest, deep learning. That'll all be contained in that folder. And I'm just going to go through 3 of those 4 with you, and then Arno, after lunch, is going to be taking on the last one, deep learning. And what I wanted to do was just introduce you to the algorithms to give you a sense of what they can do. So in a generalized linear model context, one of the nice things is that we just don't do, say, logistic regression. We have the ability to form an elastic net penalty on top of that logistic regression so you can create more robust models in a predictive setting, because lots of times you might have overfitting of your data because you weren't able to sufficiently remove out some of the redundancy in the model or the specificity to a particular data set in the model. So I just wanted to in that context, so we, for those of you who haven't heard of elastic net, you might have heard of something called ridge regression or lasso, which has to do with adding a penalty term on the coefficient side. So these are linear models, and you probably, if you haven't heard of generalized linear models, if you could think back to maybe your early stats days or even math days, you had this combination of things where you have a slope and an intercept, and maybe you might have multiple coefficients. So that's the framework we're dealing with here. Is you have this notion of a slope and well, yeah, intercept and many slopes across many features. So that's the framework. Well, imagine on each one of those coefficients, you incur a penalty because you want to keep them small. Because large coefficients might suggest that you're overfitting based upon, or you're being too suggestive of the data that you have in front of you, and you won't be as useful for the next round of data that comes along. And so we're going to incur a penalty. Either we're going to look at the absolute value of that coefficient and have a penalty associated with that, or we're going to square that coefficient and have a penalty associated with that, or some combination of the two. And that's the framework that we're going to be living in. And so if we look, this is in R, the function args can show you the arguments of a function. So if you look there at the bottom, you'll see the x and y. So those are your predictor variables, your target variable, and then you'll have the key, which is what the results are going to be stored in your key value store in the cluster. You have family, which is the error family for your generalized linear model, and link function associated with that family, and cross-validation, alpha, which is that mixing parameter. Maybe now's a good time to pull up the help file to give you more of a description on each of these. So here I'm pulling up the help file for generalized linear models. And you can either use the question mark or the help function to do that. And there'll be an explanation of what's in here. And where H2O is able to differentiate itself is in the number of models that it can fit in a relatively short amount of time. Lots of cases when you're dealing with a situation with a large data set, you might only have time to fit one model, and you could take the results or leave them, but you don't have much else you can do. What we're going to allow you to do is to fit lots of different models under lots of different settings and give you a chance to see what works best for your data. So here is some of the arguments walking again. So we have the error family and the link function. I'll leave those as details for background in case you don't know them, you can read up on them, because we're going to be working with some of the others that I want to spend a little more time on. So the notion of cross-validation, you divide your data set into equal parts, and then you leave one part out, fit a model, use the remaining part to figure out how well that model works on data that wasn't part of the training process, and you loop through those. That alpha is the alpha parameter serves as the mixing parameter in the context of the elastic net. The strength of that penalty that you're going to add to the generalized linear model is the lambda parameter, so that if you set that lambda parameter to 0, you're basically saying don't penalize at all with either the L1, which is the absolute value, or the L2, which is the square of the coefficient estimates. Then we have, so there are a number of parameters that are related to that. The epsilon parameter has to do with what constitutes convergence. So as you go from iteration to iteration, what do we use to determine whether or not you've converged? There's information on whether or not you standardize your variables prior to model fitting. And I think I'll leave off some of these in the interest of allowing you to instruct me as to what in this list you might have any questions on. If you're comfortable with these descriptions, we can move on to the next algorithm, which is the gradient boosting machine. So I'm going to open it up now to the floor for questions on this. Also in this script, it shows how you can run it. At the very bottom of each of these files in R, there's example code for running the model fitting functions. There's also, a longer demonstration that you can run using the demo function, and that's all described in that markdown file that I have. So are there any questions about generalized linear models? Yes.
Does this implementation of GLMs also include things like warm starts that are included in Hasty's GLMnet package?
Yes, yes. And so warm starts is the notion of we're going to be fitting lots and lots of models using generalized linear models. And what the warm start will allow us to do is, rather than starting essentially from the beginning, which might be at 0, you start from the last known estimates for the coefficient values as we move through the parameter space. Mm-hmm. Yes, so, and that adds to the efficiency in our code.
Okay. And also, is there, does this implementation also have the full path solution for tracing out like the optimal lambda that you get in cv.glmnet?
Well, we provide you the technology to do that. And oh, yes, yeah, the answer is yes. Yeah, we have that in there. What we don't have is that nice little graphic that comes out.
Okay.
We currently do not support weights in the generalized linear model function. It is in the roadmap, yes. Yeah, and it's something that hopefully in the near term it will happen. Any other questions? All right, we'll move on now to gradient boosting machines. So this is, for the GLM, one of the things we're known about is for our speed. For gradient boosting machines, we're known for having very highly predictive models that are being fit at scale. And so for those of you who are familiar with gradient boosting machines, well, for those of you who aren't familiar with gradient boosting machines, you might have heard of things called decision trees. And one of the problems with decision trees is they tend to be highly variable because it's a very greedy algorithm. So they tend to be highly variable to the splits that occur. And so they tend to be very coarse predictors. And so what the gradient boosting machine allows you to do is it allows you to essentially fit in a sequence of trees where one tree learns from the other as to where the previous trees have fallen short of your actual prediction of your data. It's a way of, it's a simple way of essentially putting together different trees where you're taking the residuals from previous tree fits and aggregating them together to form a stronger predictor. And what we're going to do now is to look at the various knobs and dials that we have for the gradient boosting machine in H2O. So some of the important things to have in H2O, some of the important things in this gradient boosting machine framework to have control over is the number of trees that you have to form your predictor. And so that's going to be regulated by the n-tree arguments. And another one is how deep do the trees go? Because if you have certain effects in your data, so if a lot of these, so we talked about interactions a little earlier. If you have highly interactive terms in your data, you have to make sure that each of these trees go deep enough to capture that. If they don't go deep enough to capture that, then you might miss certain features. So by default, we assume essentially four-way interactions or interaction depth of 5. So getting down to 5. There's a parameter that you can use to control when to stop splitting. So what's the minimum number of observations that you're going to consider a split at as you grow your tree? There's a learning rate that you can add to each of these trees, which is the shrinkage parameter. There's a notion of the number of bins that you can form for your numeric variables. We have a flag for group splitting. And what group splitting allows you to do is it allows you to control how categorical variables are handled. When group split is true, what we do is we take the categories, we order them relative to the response variable, and then we walk down that ordering to look for the optimal split at each of the nodes in the tree. If that's false, it's a one versus rest type of situation where you'd look at one group relative to all the other groups. There's the importance measure, which is similar to the importance measure. Well, no, actually, I think Amy did show this for gradient boosting machines, so it's that same importance measure that you can get out of it, whether or not you want to have cross-validation, or if you want to have a holdout data set that you use for validation. In a classifications framework, did you want to upsample or downsample your data so you have balanced classes, so you have 50-50 representation of each of the classes, and a parameter related to that, the max after balance size. So that's kind of walking through the parameter list for a gradient boosting machine. Are there any questions relating to those parameter sets? Yes, question. So currently, no, we do not allow specification of different loss functions. I know that, so Cliff was the author of this. I know Cliff has been looking at different loss functions, particularly in a classification framework. I don't know where that's in its stage of development, but I would anticipate seeing more loss functions. Is this for classification or regression? Both.
Both, yeah. I mean,
Okay.
Quantiles is a really nice one. I use it
Okay.
a lot. But the R's or GBM one, they have all sorts of crazy functions, and they're pretty handy here and there.
Right, yeah. So we'll be adding more to this. And a lot of these types of enhancement requests, you can mention them now, but you can also send requests to support, and we do collect them and then add them into our roadmap.
One other one is like adding trees. So you can grow it pretty short and then just kind of CV test when the right stopping point is.
Okay.
I don't see that in here. Is there a function to do that, or do you just specify the number of trees?
Well,
and then you're done?
so the question has to do with right sizing of trees. How much interaction really is in your data. What we allow folks to do is what we call perform a grid search over the parameter space, and then use a criteria that you find most appropriate to select the model based upon that. So let's say that you wanted to explore trees of size 4 through 8. You can say, interaction.depth, open parentheses 4, 5, 6, 7, 8, close parentheses, and now it'll fit models under each of those conditions that you can explore. And I don't know if I have that exact example, but I have a different example, I believe, where I give a set of parameters to look at, and then it explores the space, and it allows me to select the best one.
So you automatically select the best one from the very
Yes, according to a criteria of your choice. Now, whether we have the criteria you want, I don't know, but we have a set of criteria that you may find useful.
For the gradient boosting, when you're testing or evaluating the results, is it on holdout data? Like, is it best to have a series of 10 trees, 500 trees, 2,000 trees? You're doing that kind of grid search?
Yes.
Evaluation is evaluation on holdout data as opposed to training data?
So it will all depend upon how you have it set up. If you supply a validation data set, that'll be used. You can use cross-validation. So it'll be your preference as to what constitutes, measure of error for a general term. Yeah. Question.
Back to the grid searching for the parameters. So if the algorithm is already, if the computation for the algorithm is already distributed in the cluster, does that mean the grid search itself is not parallelized because the threads are already doing distributed computing?
So for GLM, we have this thing hyper-parallelized all over the place. I believe for GBM, though, and I'd have to check with Cliff on this, it does them serially.
Okay, so if your grid search is a Cartesian product that's of 10 by 10,
Which
you
is
have
what?
100 grids.
Yeah, we only do Cartesian products.
Yeah. So those 100 runs will run serially.
Correct. Yes.
But each individual run is distributed.
It is distributed parallel.
Gotcha.
But GLM is a special thing that when we do grid search in GLM, we do something even more clever than that. Question.
So another one, just looking here. So when you go score your algorithm, like in the regular in the RGBM one, you can specify a number of trees, which is handy because if you've put too many, then you can kind of back it up and sort of see where your kind of where your inflection point is. Is that in here? Sorry, I don't have enough familiarity with it.
So I know that you can add trees. I don't know how easy it is to remove trees because you could build off of it. So
at the 300th point, because you kind of save all the data to figure all those trees out anyway. But okay.
I'll have to double check on that because I honestly don't know what it would take to essentially say, well, I fit 300, but I really only wanted 50.
Okay.
So
yeah,
I'll have to check on that.
Okay. That and the other question about like adding trees. I mean, either one just helps you not have to settle on exactly your parameters at a time. You can just write a little loop that keeps going, and it helps you save a lot of time that way.
Now, I know you can hand edit the model, but like once you did that violate the warranty? I don't know. So it's one of those things that I'd have to look. I'm sorry, what? It is something Salford Systems does with FreeNet. Okay. It's not a complicated. It's just an implementation, issue. So if we don't have that feature, it's an easier one to add than some of the others. Question.
Hi. Do you have any tools to explore the model, like partial dependence plots, so that you can take each, let's say, predictor and see how it correlates to the target variable?
So we don't have partial dependence plots, but one of the things that I want to focus on is these types of tools. So people can make informed decisions on, other than just looking at outcomes, looking at other types of measures to determine whether or not.
Absolutely. And plotting is sometimes easy, but computing that intermediate matrix that will produce the plot is actually very
Right.
intensive.
Yeah, and that's something that we'll be considering because we want to make these richer, give a richer experience to the modeling process. Okay. In the interest of time, I'm going to move on now to random forests as the last of our trio. So random forest has a lot of bells and whistles on it, one of which is the notion of how do you calculate loss. But this is going to be somewhat similar. There'll be some overlap in terms of the notion of the tree that you have in parameter settings. Now, you're fitting a very different model here for random forest. So random forest, you're trying to create trees that are unrelated as possible from one another, but have a good enough understanding of the data by themselves that when in aggregate can produce a useful estimate. And so in the nature of that randomness, so this could be used in a classification or regression setting. Again, we have this notion of number of trees and how deep the trees go. Hold on, let me make this live here. So we can look at, in order to induce randomness in the trees, we're going to do some sampling at various different ways. So one way is for each decision that we make in our decision tree, how many of the variables are we even going to consider? And that's by the M-tries argument. When we do binning of numeric data, how many bins to use? There's a random number seed you can set. Again, a notion of importance that we have. Cross-validation, which might not be as relevant in the case of random forest because you can look at your out-of-bag error. But even if you do like using cross-validation, we have the ability to do that. You can look at also having a holdout data set for validating a model. How many nodes to use in your calculations, whether to upsample or downsample. And the notion of, again, group splitting, how do you consider categoricals, a division of categorical variables. There's that, notion of, what loss are we looking at here? Are we looking at entropy, Gini, or Turing in the case of a categorical model? Whether or not we want to do things like calculate out-of-bag errors. So here's the suite of things that we can do in our random forests. Are there any questions about this set of parameters or these capabilities? If I've exhausted your questions, or if you have questions later on, you can ask them. So if there are no questions, we'll just, oh wait, question. Okay. Right. Right.
I said before we do a lot of work with SQL Server and we do a lot of work. So let me go back to my statement. One of the first questions I asked is, do you do work with SQL Server?
Right.
Which we tend to store data in a normalized fashions for compactness. If I have, if I do my work with the H2O parse data object and I have, say, another H2O parse data object, do you guys have sort of merging tools available, or is that in the queue?
That's in our to-do list. So we do not currently have any merge or join capabilities.
Okay.
And then we have to figure out what type of merge or join are people looking for.
Yeah.
Because big to big,
Yeah.
there's a lot of effort there, and there are tools that do that quite nicely.
Oh, yeah.
Maybe small to big, what might be the first on our
it's
list.
definitely not trivial.
Yeah. But it is something that we've looked into, but it's not where we focused our efforts at the moment.
Okay. All right. Thank you.
But it is on our list. Okay. Oh yeah, question. All right.
We get the matrix of votes for each class from just like a regular random forest package does.
So you want, what you can get is the probabilities for each of the, oh, you're saying for each tree?
If I say, like,
that,
I 100 trees. And
yeah.
I want to say 100 from the matrix. So
I know that we can give you the probabilities for each of the classes. I'm not 100% though on each of the trees. I don't know if somebody out there might know, but I'd have to look into that. I honestly don't know. That's something, again, it's easy to add. I just don't know if it's there. And it's something we can explore when we come to the predict function. All right, so just looking at time, we have roughly 45 minutes that we're going to walk through these scripts. We'll see how it goes. If you have questions along the way, please don't hesitate to ask. But I want to make sure that we all have time for lunch. So the way that I broke this up logically was just into regression and classification problems. Because that's how people algos are a means to an end. And so I wanted to break things up into, what is the problem that I have what is the problem I'm trying to solve, and what tools do I have to solve it? So in the course of these scripts, I don't go through the process of really going deep dive into what each of these algorithms do, but rather what do the byproducts look like in R, and how do you operate on those byproducts? So all I'm going to do is I'm going to, now for those of you who have a session already running, the data will probably be available, your cluster will be running, but I'm just going to restart my cluster so I have something functional. And I had conveniently saved off the data for reuse, and I'm just going to read in the test and train data sets. Again, if you already have these built from the previous exercise, you won't have to do this step. And one of the things I'm going to do is I'm just going to stash off a particular column with a named key. So the idea here is that we're going to try to predict wages on a log scale. And the reason why we're doing it on a log scale is because it better works with the algorithms that we have. In the next exercise, we'll look at a classification setting. But we'll just look here at wages on a log scale and see how well we can predict them using various algorithms. And as before, I'm going to take some integer-coded data and say that it's categorical. And then I'm going to, I thought just for fun, I'd create a column of random numbers and just throw that into a model just to see what comes out of it. Number one, to just put into your mind that sometimes when you think there's a signal, it might just be noise. So I just generate some random numbers. I break them into 100 categories, and I'm going to use that as my first predictor. Not because this is going to produce an awesome model, but because it'll give me something that I can play with this is what I'm going to play with during modeling. I've just been given notice that I'm about to wrap up. So I apologize for that, but I'm just going to walk through things somewhat quickly. The scripts are here for you. If you have any questions, do let me know. But the thing that I wanted to reinforce is that these objects inside of R, you can compute on the resulting objects, just like you can compute on the resulting R model objects. And here I'm doing things like, well, I fit a model. Tell me what the tell me what the structure of the model is, what are the names of the components of the model, what are the coefficients, some of the statistics that you have. I can do things like calculate aggregates. In this case here, the aggregate happens to be a model summary. It's the mean squared error for the model. I can go through the process of fitting a cross-validation. And this is where I'm starting to fit multiple models here. So I'm fitting a tenfold cross-validation. I'm just going to start talking and going through this rather quickly because my time is running short, and I apologize for that, but the install took a little longer than expected. So I actually fit 10 models that I'm going to look at some of the results for. And the picture, you can look at the picture on your own online just to get a sense of, for each of the 10 models in my cross-validation, what were the coefficients, how did they look? I think I'm going to skip through this piece here. I want to get to an interesting bit where I get to the process of actually fitting a grid search. So this is where grid search starts to creep in. And just due to time, I apologize. I don't think I'm going to get a chance to go through all of this with you. But what this script is going to, what this function call is going to be illustrating is what does it look like when you fit multiple models using a grid search, for a particular algorithm. It's going to do the Cartesian product of these specifications. So I'm going to fit lots and lots of models, and based on those models, I'll be given some tools to select what the best one is. And so here you see the progress bar creeping across now. Keep in mind that I'm fitting 10. I have 5 alpha settings, so that's my mixture parameter. I have 10 lambdas, which is the strength of the penalty. So 5 by 10 is 50 different models that I'm fitting here. And this is a decent-sized data set. This is 112,000 rows of data. And it's fitting very fast. And this is even on a virtual machine. I think I'll skip off of some of that and just talk about, let's see here. Well, let me just take my hands off the keyboard for a second. Oh, yeah, I'm getting notice here. What? Am I done? All right. All right, people are hungry. I apologize about some of the issues relating to the installation. I'm sorry we didn't get through all of my material. Please look through what you have. I'll be here. You can ask me any questions that you might have, and enjoy your lunch.